So for the introduction of Chapter 7, I really wanted to review for you a concept that you learned last semester. It was the concept that related the work done by a force to the change in the potential energy of the system. The reason I wanted to review this is understanding this, I think, will really help when we're talking about the idea of potential energy in an electric field and also the change in potential. So just to review a really simple example that makes a lot of sense to us, we have an object, it's subjected to the force of gravity, and it's going to fall. If I just say it moves a distance downward delta S, the work done by gravity can just be expressed as the force mg times delta S. Since the force was in the negative direction and so was the delta S, those negative signs will both turn into a positive sign when we multiply them together. So gravity has done a positive amount of work. But when we introduced the concept of potential energy, we said that when a force does work, we have to think about where that energy comes from. That energy can be thought of as have been stored in the system. And as a result of that work being done, some of the energy that that system stored has been lost. And what we do is we talk about that stored energy and we call it potential energy. And so when the work is done by the force, we can calculate the work done, but this corresponds to minus the change in potential energy. And so let's think about what that means in the context of this expression. This is equal to minus delta U, where I'm really speaking about the gravitational potential energy. Now, the work is positive, and so we know that altogether this term also has to be positive, which means, because there's a negative sign in front of it, that the change in potential energy also has to be less than 0, which means U final minus U initial is less than 0, which means the final potential energy is less than the initial. And so it really does reinforce this idea about what is happening and sort of the flow of energy during this process. In order for gravity to do the work, which was a positive amount of work, it did use up some energy. And as a result, the potential energy that was stored in the gravitational field goes down. That is, even, we can write here, the final potential energy that the gravitational field had is actually less than its initial. Does that make sense? You think about it, and hopefully it does, because it's a very important idea and when we think about things in terms of energy. So now we're going to talk about an electric field. And as I had said in class the other day, when you see a picture like this with the arrows for the electric field lines, when they're all evenly spaced and straight and all pointing in the same direction, we're representing what we would call a uniform electric field. That means that the electric field has a value, I don't know, maybe it's 5 newtons per coulomb, and it's 5 newtons per coulomb no matter where I go in this region of space. Now, I'm going to tell you one of my pet peeves. When we talk about this electric field, we want to just talk about the electric field. Now, I know that we did learn that the electric field points towards negative charges and goes away from positive charges, but I want you to not even think about the possibility that there are some charges over here, and I want you to concentrate on the field. I also want you to remember that the way that we defined the electric field was we imagined putting a test charge near another charge and then calculating that force that the test charge would feel, and then we took that force and divided by the test charge and we were left with the expression for the electric field. Now, something handy comes in if you take this expression and you rearrange it. And that is, if I place a charge in an electric field, the force is just equal to QE. It really comes in handy. So, I'm going to imagine I put a positive charge in this electric field. Now, the first thing that I want to ask you is, what is the force that that charge is going to feel? Will it feel a force to the right or to the left? And we can use this to help us out. From that expression, as long as this charge is positive, the direction of the force will be the same as the direction of the electric field. And this is a positive charge, and so the force will be in that direction. Now, this is where I really want you to be able to think about finding that force using those steps of logic. I really don't want you to say that this positive charge feels a force to the right because there are some negative charges over here. You don't know that. They're not there, so stop saying that. Think about it just in terms of the charge being in the electric field. So, if we imagine that this charge goes from here, this is its initial point, to here, and so this is its delta S, we could say that the work done, and I'm going to here, is equal to QE times delta S, and those both were in the same direction, and so that work was positive. And because this work is positive and it's equal to minus the change in the potential energy, we will then also have to say that the change in potential energy has to be negative, because we'll have this term be negative times this negative sign will give me a positive. So again, see how this is very similar to the example with gravity. When the electric field was allowed to do work on the charge to move it to the right, it was using up energy to do that work, and as a result, its stored energy, which is potential, would decrease. All right? What about the case where if I take a positive charge, it feels a force like this, but what if delta S is like this? Is that going to happen spontaneously? Will that just happen? Or do I have to make it happen? Think about that. If I place my charge, my positive charge, in the electric field, will it be able to move to the left? The only way that it's going to move to the left is if I have some external force acting on it. Because its natural inclination would be to feel the force of the electric field and move to the right. If it moved to the left, there must be some sort of external force to make that happen. But if, in any case, if I was calculating the work done by the electric field, that work would be negative work, because honestly, this force is not going to do anything to make it go to the left. And so when we think about this being equal to minus the change in the potential energy, this actually has a potential energy change that is greater than 0. Why? Why does it have an increase in its potential energy? It's because there had to be an external force. This force actually had to do the work to move this positive charge to the left. The charge does not want to go that way. And so that external force in doing that work was giving its energy to the system, and that's why the change in potential energy is greater. And so one of the things that we want to think about is we kind of notice for this positive charge is as we go to the right, you know, sort of moving to the right resulted in a decrease in potential energy, and moving to the left represented an increase in potential energy. Now, part of the reason that we get those values for the potential energy is it's sort of an interaction of the charge with the electric field. And what we would like to do is to just think about the field itself. And so if we think about the field itself, what we do is we talk about the change in potential, which is the change in potential energy divided by the charge. Because if you do that, because this was equal to QE delta S, and I divide by Q, notice the Q doesn't have any effect on that change in potential. And so what this becomes, sort of the way we can think of it, is it's a characteristic of the electric field. And that is, the idea is when we move around in the electric field, we actually go through changes in potential. Of course, it only really applies, and we'll talk about that in more detail in class, where it really is mostly when we move either with the field or against the field. But using this idea, what we could say is as we go from, if we go with the field, and if we were moving to the right, we're going from higher potential to lower potential. So we got higher V here and lower V here. And there's actually values for that potential, and we're going to look at that more when we get into class, but I wanted to introduce that to you, you know, so like it wasn't the first time you saw it when you saw it in class. Of course, I know you're reading the book, so you see it there too. But what we're going to want to think about is, you know, another way to think about that electric field is that within the field there are different areas where the potential due to the field is different. And when I move a charge from one point to the other, I'm moving it from a point of a higher potential perhaps to a lower potential, and then this influences the change in potential energy that that charge experiences. But the potential is something that we like because it's only really talking about the electric field, and it's independent really of the charge that you place in the electric field. So hopefully this made a little bit more sense, but what I wanted you to really have a review on is this relationship between work and potential energy, and start to apply it to this new situation that we're working with, the electric fields and charges, etc., because that's what we're going to be looking at in Chapter 7.